question paper 2 of year 2021. Question number 2b is a thin hollow stainless steel tube with inner diameter 7.6 mm and outer diameter 8 mm is heated with a current of 250 ampere intensity. The outer surface of the tube is insulated and all the heat generated in the tube wall is transferred through its inner surface. The specific resistance and thermal conductivity of steel are 0.85 micro ohm meter and 18.6 watt per meter per degree Kelvin respectively. Calculate 1 volumetric rate of heat generation in the tube and 2 temperature drop across the wall. So first of all, volumetric heat generation, that is your I square R. R is resistance, I is current, and resistance in terms of this specific resistance is given as rho L into A, where rho is a specific resistance, L is length, and A is area. So this is the total volumetric heat generation. So if we want to calculate heat generated per unit volume, so we have to divide by volume. Volume is your A into L. So this will become rho I by A square. So that is your volumetric or heat generated per unit volume. Okay. So now we can put the values. That value is given, that is 0.85 micro ohm meter. So that is 0.85 into 10 to the minus 6. I is 250 ampere and A is area of this cylinder. As it is hollow, so it is pi by 4 8 square minus 7.6 square in meter in mm square. So we divided by 1000 square, then it will be meter square. Okay. So solving this, we get heat generated per unit volume as 2214065 425 watt per meter cube. Okay, so this is the volumetric heat generation, or answer to first question. So now the equation of heat transfer with heat generation is in general coordinate is 1 by Rn dr raised power n dt by dr is equal to minus qg by k. So here if we take n is equal to 1, then it means cylindrical coordinate. Okay, so taking n is equal to 1, so this cylindrical coordinate. So the equation will become like that. This 1 by R will be there. This R can come here. D by dr within bracket R dt by dr is equal to minus qd by k R. So if we integrate it, it will be R dt by dr, and this will be minus qd R square by 2k plus C1, and this will be dt by dr is equal to minus qd R by 2k plus C1 by R. So this is equation number 1. Now if we again integrate it, it will be T is equal to minus qg R square by 4k plus C1 log e R plus C2. So this is equation number 2. So this integration is given in book. Okay. So now the boundary condition are that outside surface is insulated. Tube is insulated. The outer surface is insulated. It means at R is equal to R2, dt by dr is 0. So this is 0. So from this we can get C1, that constant. So that constant comes out as, because we have put here, so that constant comes out as qg by 2k R2 square. Okay. And now at R is equal to R1, temperature is for T1. So T1 is this, putting value of C1. So now we can get R as R1 and this is T1, and from this we can get the value of check-in constant, that is T2. So T2 is equal to T1 plus Qg by Q2 within bracket 1 by 2 R1 square minus R2 square log E R1, and the general equation will become now the expression for T is this. So we can put the value of T1 and T2, so we get this equation. So now if we put R is equal to R2 and the temperature at R is equal to R2 is T2, then we can put this here T2 and putting R is equal to R2 here. Okay. So now we have value of T1, inner temperature given, outside radius are given, Qg we have calculated. So we can put these values and find the temperature drop. So T2 minus T1 is equal to this. Now we can put these values and find out the temperature drop. So that comes there 2.42 degree Celsius. So that is the answer to that question.